Hello, everyone. Thank you for joining us today. I am Camilo Castrillon, intern from the chemistry team, and with me, Jason Sonnenberg, Wolfram Chemistry developer. We want to give you an overview of what's new in our chemical education efforts since the WTC in 2021. So let's get going. This is the abstract only included for archival purposes, so let's go to the next one. We have a large collection of tools, and we just heard Jason Biggs talking about the Wolfram Pipeline repository. There is also the Wolfram Demonstrations project, where you can find almost 1,000 demonstrations in chemistry education. The Wolfram Function Repository, where new functions have been added to the repository this year, mainly for biomolecule visualization, increasing the number of chemistry functions to 36. The virtual chemistry laboratory that helps students in practicing with real-life scenarios, and the Wolfram data repository, where students can find useful information for solving chemistry problems. We'll focus on some new features in Wolfram Alpha, the Notebook edition, and the Wolfram Language. We'll start with Wolfram Alpha as new content has been created. We've been doing a lot of effort with chemical reactions, so 209 named chemical reactions have been added to Wolfram Alpha. Here we have two examples, the Friedelscraft calculation, a reaction widely learned by chemistry students from around second or third year. So we have descriptions of the reaction, alternate names, and classification of the reaction. Down here, we have some reaction details like the reactants and solvents and catalysts involved in the reaction, as well as the products obtained by the reaction. And finally, a bit of history, the scientists that discovered the reaction and the discovery date. Also, the Wikipedia hits history throughout the years for this reaction, and same thing for the Diels-Alder reaction. In this case, we have an award section for the Nobel Prize related to the scientists. Again, these are two examples of the 209 named chemical reactions in Wolfram Alpha. Since 2021, the team has focused on chemical reactions mainly. Now, we're moving to new things in step-by-step content. Remember that step-by-step in chemistry is the automatic generation of keys for solving chemistry problems. I added steps for ionic reactions. These steps give support for calculating the total ionic equation, the net ionic equation, and the spectator ions. Let's take a look at the steps for the net ionic reaction. Here you would have the chemical plan for what you would need to know before solving the problem. The plan step contains a strategy for solving all problems belonging to this particular class of chemical problems. This is one aspect of chemistry steps that make us different from math step-by-steps and also from our competitors. So let's take a look at the rest of the steps. Always balance the chemical equation at the beginning of the problem. After that, every compound that is aqueous needs to be separated into its ions, and solid compounds should stay the same. The next step would be to identify those ions present on both sides of the equation and mark them as spectator ions. As you can see, the steps for calculating the total ionic equation are contained in the net ionic equation, and these steps for net ionic equation are also contained in the spectator ions steps. So let's move to the property comparison option. This option is made by Jason, and this option lets the user ask for a property for multiple entities at the same time. Here we have an example looking for the molar mass for 4 entities. Here we get the results for all 4, and we can display steps for each one of them. As you can see, here we have the drop-down menu, and it works only for the entities that we have steps for. So in this case, the lithium, we don't have steps for the lithium since it corresponds to an element. Let's move to the quantity arithmetic. This property is made by Daniel. So we have arithmetic operations like adding 2 quantities with different units. So we get 2 results, one for each different unit. If we click in this step-by-step button, we get the steps for the inputs. And similar to the property comparison, we have here a drop-down menu that shows steps for each of the units. Down here, we have some units comparison and also comparison as activation energy. You'll hear more about it in the next talk. So the steps shown here are available all in Wolfram Alpha. The steps for the ionic reaction, the property comparison, and also the steps for quantity arithmetic are all available today in Wolfram Alpha. Let's move to calculators. So calculators have been increasing by adding 2 new ones for a total of 56 calculators in chemistry. They are all available today in Wolfram Alpha with many other calculators. So here we have the computational inputs where the users enters the information that needs to be calculated. Down here, we have the equations used by the calculator and the description of each variable. A bit further, the input values entered by the user, and finally, the results with steps for different magnitudes. Here we have also the drop-down menu that shows steps for each of the units. Same process for the second example. And let's move to the final new thing. So significant digits are an approximation to the full error propagation learned in the 3rd or 4th year of chemistry, both topics suitable students and researchers alike. In the Wolfram language, error propagation is achieved via a round and a round replace. So with those functions, we are able to bring full error propagation to all Wolfram Alpha chemistry computations. So here we have an input for the lithium-7 isotope, and we are asking for the atomic mass. And we get the result that in the last digit, there is uncertainty, and for the rest of the properties as well. You can have error propagation in chemical quantities, like here, we are having a quantity with uncertainty of rhombic sulfur, as you would do in a regular basis at the laboratory. And as you can see, same thing with the error propagation in the properties down here. Also, in chemical conversions, you can ask for example, a quantity in milliliters of potassium hydroxide with uncertainty, and you would get the result with the corresponding uncertainty in milligrams. And by clicking the step-by-step button, you can see all the process for calculating the final result. This is everything that I wanted to show you. So let's move with Jason with the notebook edition. Thank you.
Thank you, Camilo. Now let's turn our attention to Wolfram Alpha Notebook Edition. We've been just as busy with the Wolfram Alpha Notebook Edition functionality as we have been with Wolfram Alpha. And let's start with the new functions. We now have chemical formula support. So here we're putting in a dithorium sandwich complex and asking for its molar mass. And you'll see that we convert immediately into the chemical formula as a string, and then we ask for the molar mass, which is computed and returned as a quantity. Chemical conversions have seen a lot of effort. Besides being able to do chemical conversions, we now have the ability to pass in an uncertainty with our measured value. So here we have 5 plus or minus 0.001, so 1 milligram air iridium, and we're asking for the amount. And that is converted over to a chemical convert function with a new chemical instance functionality where we have iridium and the amount that was measured out. And then the second argument here is asking for what we're looking for, which in this case is amount. And that returns another chemical instance of iridium where the mass is now being converted to moles and the air propagated under the hood and carried along in the answer. We have support for showing the details of how to do this conversion if there's uncertainty present. And so as you see here, you just append show steps to your original input, and then you can get the step-by-step details for carrying through the calculation with having the uncertainty propagated through. We've been adding support for Wolfram function functionality from the repository system. So here we have the ability to ask for an IUPAC name. So here I've got a smile string that I was using in my work and didn't know what the IUPAC name was. So I asked for it, and that gets converted into a molecule that's passed on to IUPAC name. And IUPAC name goes out to PubChem and returns the first IUPAC name for this molecule that it finds. We have support now for molecule value plots, so you can ask for things like the labeled hybridization diagram, and you'll get the molecule value plot of the particular molecule, in this case ATP, and we see that the orbital hybridizations are returned. And in the resulting plot, you've got the atoms highlighted by their orbital hybridization as depicted in the key. We're always looking to improve our natural language, particularly in chemistry, and so we've added some shortcuts. You can just say 2D plot of and give a molecule, and you'll get the 2D molecule plot result of that molecule. Three-dimensional plots are easily accessible now using 3D plot of X. And here, we again, that same molecule, and we see that we get the molecule plot 3D results that are completely rotatable and ready to use by the student inside of their notebook. So Wolfram Alpha Notebook Edition has a lot of functionality that's particularly useful in early classes in the curriculum. So maybe your middle school, high school, first year courses in college. And I'd just like to take a moment to show you one activity that we've built to see how this technology could be used for an interactive activity that you might use in your classroom. So here it's the title, Exploring Atomic Electron Representations. And at the top there's space. Again, these are Wolfram Alpha notebooks, so you can put text and bullets along with input cells. And so we can lay out the prerequisite concepts for both the instructor and the student, along with the learning objectives. And you can also include the accreditation requirements for the particular activity. In this case, it was designed for a college chemistry program. So here we have the American Chemical Society Committee on Professional Training Standards, a statement of academic integrity for the student to sign, and then we have the activity, which is a combination of instructions with computational fields to do calculations or pull up data. Here you could say, I need a periodic table, and the student would hit return and then pull up a periodic table right there in their notebook. As they work through the activity, they will be, pulling up data and answering questions, filling in their answers in these gray boxes here. And as the student gets through all the activities, they would, presumably turn this in, or maybe do group work with it in a sort of classroom learning environment where maybe you're doing group work in class. But as you can see here, you can mix and match the content. It doesn't have to be just text. Here we've embedded a demonstration that shows how an alternative representation of the electronic information about each element. And of course, a question at the end for the students to fill in and show their chemical thinking. So this is just one of many possible ways of using the tools, but we just wanted to show you so you could see how this technology can be rolled into your classroom. Now, Wolfram Alpha Notebook Edition bridges the notebook environment to the language environment. So let's turn to the language environment. As you can tell, we've had 14 new functions since the last WTC. So this puts us at 41 functions. Most notably, we've got a lot of support in chemical conversions and chemical reactions. We've already seen chemical convert and chemical instance. We'll talk about apply reaction, pattern reaction, reaction balance, and the chemical reaction object itself. So let's move forward. In an upper level class, you might be working with Wolfram notebooks directly, and the students can access chemical formulas quite easily. It's the chemical formula head, and you pass in a string. Here I've got a uranyl complex that is common in my research, and so it is turned into an object with appropriate formatting. Chemical conversions are equally easy to do. Here I'm defining an instance of a chemical, so this allows me to define my chemical and the amount that I have. Here I've defined it as a quantity with an around object, so I can carry through the uncertainty in my measurement. Here this was half of a milligram uncertainty. And then in my next line here, I can do the chemical convert to do the chemical conversion of this barium sulfate and change the grams into millimoles. And what you get back is another instance of barium sulfate. along with the new value that you are after, the millimoles. Reaction balancing is straightforward too. Here I'm going to define a reaction object, the chemical reaction, and I'm going to put in this particular redox reaction. And I have used the text input rather than an object input, and you can see the different ways of indicating charge, the caret superscripts, or just directly after the chemical species. You can feed this chemical reaction to reaction balance to balance it. That would spit out a new chemical reaction that I'm immediately going to ask for the equation display for, and we get the balanced chemical reaction here in print form. We could have asked for the chemical reaction object, but I just stopped with the display. So all very straightforward in a short amount of text to balance chemical reactions. Building on the new functionality for chemical reactions are the ability to explore chemical synthesis using pattern reaction and apply reaction. So here I've built an interactive manipulate with manipulate function, and I'm going to look at the hydrohalogenation of alkenes. So an alkene is a molecule with a double bond, and we're going to add, in this case, hydrogen iodide across the double bond to make a new molecule. What's important here is under the hood, we've defined the pattern reaction, and the manipulate is applying that reaction. For those that may not recall, what this reaction does is that across this double bond, the double bond is broken, the halogen, in this case iodine, is added, and the hydrogen is added to the other end of the bond. So this is all being done computationally, and so with ethene, it's not particularly exciting because we're just adding an iodine. And here I'm using tooltips to show different structural information. But we can change to hydrogen bromide, and what you see is that, again, this was computed on the fly and figuring out where the bromine should go. Since we have a symmetric molecule, there's only one product. But if we go to a molecule like propylene, which is antisymmetric across the double bond, meaning that either end of the molecule is different, then we can get two different products. And that is computed on the fly and laid out graphically. If we move to 1,4-hexadiene, we get some really fun results. So here we now have two double bonds, and we have 4 different products that can be added, or products that can be formed by the first addition, excuse me, and we can run the reaction a second time and figure out which products are possible there. And here the graph underneath that's displaying this notices commonalities and connects them as such. So there are 2 different reaction paths to get to this product, to here, to there as well. But this allows step-by-step exploration of chemical reactions. This is just one particular organic reaction that's commonly taught in your introductory organic sequence, but you can build these up to do much more complicated things. Also new this year is the Mathematica and Wolfram Language Fast Introduction for chemistry students. We have 2 other fast introduction textbooks that have been published and are available on the web, and this is the next one in that series, focusing on chemistry. I'm going to switch over to the web version rather than the notebook version, so we can look at how it displays live in a web browser. So here you have, again, the same book with the QR code for quick access. And we have sections of getting started, an introduction to electronic notebooks, input, short discussion of fractions and decimals and variables and functions. And then we get to chemistry. And we talk about the chemical representations that are available inside of the language. Atomic representations, mass composition, structural, explaining how to get started as a chemist in the language and our notebooks. Then we have examples for atoms, chemical formulas, molecules, biomolecules, and the chemical entities. We go on to talk about data and measured data and how to deal with quantities and units. And then we go through a brief topical survey, which is ever growing as we add new functionality in the language. One fun one is stoichiometry, where we can work through a stoichiometry problem. using the tools that are now available with chemical instances and chemical conversions to figure out what the limiting reagent is in this particular reaction. All of this is available online and available for download for use in your classroom. The Wolfie stone might be particularly useful, a little pun on the Rosetta Stone, but it's a nice quick reference from going from the chemical object to the representation in the language. That may be quite helpful for getting yourself and your students up to speed on using our tools in your educational and research efforts. So that's the fast introduction for chemistry students. We hope that that will be quite useful in a growing project over the next years. So to conclude, I have some useful links. The core areas for the Wolfram language, the link to the chemistry page. Our new online dilution calculator, which is one-stop shopping for doing chemical dilutions, both doing the calculation themselves and a bit of background for the student to understand which formulas to use and such. Again, here's the link to the fast introduction that we just looked at, and the link to our ever-growing Wolfram chemistry resources. That's a curated list maintained by the chemistry team. And with that, I'd like to thank you for your attention, and we'd be happy to answer any questions you have.